Welcome back, everyone. We hope you enjoyed the first session and are ready for another power-backed discussions. Our second session is on understanding data, probability, and statistical thinking for ML. We are privileged to have with us Dr. Bindu Krishnan, Senior Statistician at IBM Kochi, Kerala, with an outstanding 25 years of industrial experience in the field of data and artificial intelligence. Now, to introduce our distinguished speaker, I would like to invite Mrs. Archana CS.
Good evening, all. I'm delighted to introduce our speaker, Dr. Bindu Krishnan. Dr. Bindu holds a PhD in statistics and MTech in data science and AI. She is currently a senior data scientist at IBM India Software Labs, Kochi, as a role she has held since 2022. Her career spans more than 20 years of teaching, industry, and research experience, including leadership positions such as professor and head, Department of Data Science, CS, and IT at Jain deemed to be University. Dr. Bindu has made significant contributions to the field of distribution theory, time series modeling, data analytics, and machine learning. She is the author of the book Probability Distribution, Random Process, and Numerical Methods, published by Wiley, and has published over 20 research papers in reputed national and international journals in areas like statistical modeling, AI, and deep learning. Beyond, she is an expert in statistical and data analytics software, including R, Python, Tableau, Power BI, SAS, SPSS, etc., and is widely recognized as a resource person for workshops and FDPs in statistical modeling and AI. Please join me in giving a warm welcome to Dr. Bindu Krishnan. Ma'am, the session is yours.
Thank you. Good evening, all.
Good evening, ma'am.
Yeah, good evening. I know this time it's very difficult to.
Good evening, madam.
Yeah, learning, hearing something. Anyway, usually ATAL FDP, especially online sessions, always we can expect only this time. So pardon me for taking this time. Okay, like all of you, of course, I'm also a working person. Okay, anyway, straight away move to the session. So first of all, let me express my sincere thanks to the organizers, Betsy ma'am and team, St. Mary's College, especially principal management, for this invitation. And I'm so glad to share, especially on this particular topic. So because always something related to machine learning with connecting statistics and probability, it's my passion always. Okay, so actually the title is Understanding Data, Probability and Statistic Thinking for ML. Hope it's clearly audible, right?
Yes, ma'am.
Okay, thank you. So let me, I don't know whether to start with probability statistics or ML. So hope more participants from computer science, right? Or from mathematics statistics side?
Computer science, ma'am.
Okay, anyway, okay. So anyway, since more participants
Electronics also, ma'am.
Okay. And not from mathematics or statistics, right? So it's better to start from statistics or statistical techniques, of course, tools, statistical techniques, all of us, even a layman is aware of that. Tools that enable us to, simply saying, tools that enable us to answer questions about, say, possible patterns in empirical data. Then just connect our machine learning with that statement. Tools that enable us to answer questions about possible patterns in empirical data. So if we connect the term word machine learning to that particular statement, we can say machine learning is, compared to that expression or that statement, we can say machine learning is simply saying about developing or predictive models, developing predictive models from uncertain data. So I connected that machine learning and statistical techniques. Now one more term. Without that term, we can't define. No one in this world is may not be in a position to define machine learning without probability. So I can say I'm using the term probability is the heart of machine learning or bedrock of machine learning. Probabilistic methods, we can say, are the heart of machine learning. So as we all know, machine learns from experience or data. But how can a machine or how a machine learn from experience? Obviously, probabilistic modeling provides a mathematical framework for understanding what learning is, and therefore emerged as one of the principal approaches for designing algorithms, especially computer algorithms, that learn from data acquired through experience. And this probabilistic framework defines how to signify and deploy, say, reservation about models. We cannot develop a deep understanding of and application of machine learning without it. No doubt in that. It is impossible. Especially the role of predictions in scientific data analysis is so important in machine learning, as we all know. Not only in machine learning, then automation, cognitive computing, or artificial intelligence, and so on. A lot of terms are there. But the field of machine learning underpins recent advances in AI, data science, etc., and of course has the potential to play an important role in scientific data analysis. Okay, so I think let us have a look at just an overview of machine learning. Then I will connect these terms, probability, statistical thinking, etc., with this term. Let me share the screen. I'm sorry, I'm not well. Not well in the sense, only some throat issues. In advance, asking apology for the same. But I know if I will cancel this last minute, this organizers difficulties, all those things I know. The thing is that especially during, I usually tied up with this throat infection. But the thing is that if I continue this, maybe after 1.5 hours, my sound will go. That is a problem. Because tomorrow also I have a program at Rice College. Anyway, water is here. I'll manage with that. And please cooperate with me. So let me share the screen. Is it visible? I just shared my PPT.
Yes, ma'am.
Okay. I think the full screen visible, right? Hope so.
Yes, yes.
Okay. Yeah. So, introduction, of course, I think it's better to start with just an overview of machine learning. I know most of the participants are from computer science or especially from the engineering background. No, nothing detail about ML is required. But even though I start with this particular term ML, I'll be focusing more on the statistical part in ML. Okay. So, of course, this word machine learning, as we know, it's rapidly changing the world from diverse type of applications and research, both in industry and academia. Or we can say this is affecting actually every part of our daily lives. So, two terms, machine learning. Learning or machine means some apparatus that can perform any kind of task like a computer or printer or some device. So when we add the term learning, together it means how a machine learns. Or we can say this is a lot of definitions are there. This is the one which we can say whenever we make a Google search or anywhere. Now people are not using Google, people are using the ChatGPT anywhere. We can say this first definition, field of study. I'm not changing that. Okay, let us start with that definition itself. field of study that gives computers or devices, in general we can say devices, the capability to learn without being explicitly programmed. So learn without being explicitly programmed, which means that we are not going to teach the device or computer with a specific set of rules. But instead, what we are going to do is that we feed the device or computer with enough data. Give them time to learn. Give it time to learn by making its own mistakes and improve upon those. Okay, so we don't have any specific set of rules. Instead, we always start with data. That is why I mentioned machine learns from experience or past data. Always we begin with data. Or we can say it is concerned with development of algorithms and techniques that allows the devices to learn. Simple example, we can start with see, every day we recognize our family members and friends simply by looking at their faces or from their photographs, despite the differences in pose, hairstyle, lighting, and so on. So actually we do it unconsciously, and we are unable to explain how we do it. How do we recognize our father? How do we recognize our mother? Like that. So since we are not able to explain our expertise, we cannot write the computer program. But at the same time, we know that a face is not just a collection of pixels. It has structure. It is symmetric. There are eyes, nose, mouth, etc., 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 located in certain places on the face. And each person's face is a practical combination, or it is composed of, is a pattern actually. Each person's face is a pattern composed of practical combination of all these. Now, how a machine recognizes these patterns or recognizes a person's face? By analyzing, we always starts with data, begin with data, right? So we are feeding that machines a set of data we are actually passing to the machine, or we are feeding to the machine. So by analyzing the sample face images of a person, the learning program captures the pattern specific to that person and then recognizes by checking for that pattern in a given image. So actually this is an example of say we can say either face recognition or pattern recognition. Okay, so anyway, machine always learns from experience or past data. So we always, for machine learning, we begin with data. Now, machine learning. So as I mentioned, machine learning is actually programming devices or programming computers. I'm using the computers itself because most of the cases we are actually using computers here, but that can be a device. So machine learning is programming computers to optimize a performance criteria using some data or some past experience. And there actually we have a model defined up to some parameters, and learning is actually the execution of the computer program to optimize the parameters of model using data. So that model can be not a realistic thing. That can be sometimes descriptive or sometimes predictive. If it is predictive, we can say that model that predictive model is used to make predictions in the future. But if it's descriptive, we can gain some knowledge. Or sometimes that model can be a combination of both descriptive and predictive. So anyway, so always after passing the data to the machine, we will get a model. That model we call it as machine learning model. That can be a mathematical real representation of real world process. Or I can say one more simple example. See, Suppose I take someone of you to a pet shop. Let us assume a small kid. Suppose I take a small kid to a pet shop. Assume that that pet shop has, say, 4 dogs and 5 cats. I'm taking a small kid to a pet shop. And if that pet shop has 4 dogs and 5 cats, and assume that I try to teach that kid, that child, which of those animals is dog and which of them is cat. Okay, so assume that initially there are only 4 dogs and 5 cats. So if I teach which of them is a dog and which of them is a cat, after that, if I bring a different breed of dog, which is not present in the first set of 4 dogs and 5 cats, then that child can predict whether it is a dog or cat. Right? But please keep in mind that the second set, actually, I brought a new set of new dog, which was not present in the initial set. So that initial set, which I used to teach that child, that is 4 dogs and 5 cats, that we called as training data set, because I have used that 4 dogs and 5 cats to train that child or to teach that child. So we can call that as training data. So after teaching, I brought another dog just to test that child, that is whether that child learned or not, how to child learned to distinguish between dogs and cats. I want to test that. So I brought another one and I asked that child. So that another one, that we can call it as a test data, because I have used that second set dog only to test that child. So actually, the machine will, maybe that child answered correctly or not. That is the second thing. So machine actually works in a very similar manner. So the initial set of dogs and cats, 4 dogs and 5 cats, which I used to train that child or teach that child, we call it as training data. In the machine learning also, we always start with a training data set. We feed that training data set to the computer or machine. Then the machine learns from that data so that you will get a model. And of course, here actually I am here to learn to teach that child. But after passing the data to the machine, we usually use statistical algorithms or mathematical algorithms. That is, to generate a machine learning model, we need to provide training data to a ML algorithm that is same as statistical algorithm itself or statistical methods. So there is no machine learning without statistics, be frank. There was also, of course, that role of computer science also there. I'll come to that. There is no machine learning without computer science. I too agree with that. See, I am not saying like this, there is no machine, as I am a statistician. No, I am studying actually both statistics and computer science. The only thing is that my MTech in artificial in computer science and MSc in statistics, that is the only difference. Okay, because I am a person, since I am a person studying both in computer science and statistics, I can say equal role there for both computer science and machine learning, and statistics in this particular machine learning. Okay, so anyway, that algorithms or techniques which you are using actually comes from mathematics or statistics. So while training machine learning, so the machine actually learns same as the example that I mentioned, the case of child. So while training machine learning, we pass an algorithm with training data. Then that algorithm finds patterns in the training data such that the input corresponds to the target, and that output, we call it as machine learning model. That can be used to make predictions. And also, like I mentioned, it is not necessary that always you will get a predictive model only for, say, for example, one of the procedure which I'll show you in the upcoming slides, clustering. Clustering is one of the procedure in machine learning. Actually, clustering, while applying that clustering technique, you may not get a predictive model. Instead, that clustering actually, it classifies our data set into different groups. And that groups itself we call it as clusters. So that is why previously I mentioned this machine learning model can be predictive to make predictions in the future, or can be descriptive to gain some knowledge from data, or can be both predictive and descriptive. Right? Now, what is the difference between machine learning or machine learning versus statistics? Of course, these two things are very much closely related. Statistics and machine learning are very closely related fields. Okay, thank you. So in one sentence, I can say machine learning uses the theory of statistics in building mathematical model, right? Because the reason is very simple. The core task is making inference from a sample. But the role of computer science is actually twofold. I think CS people, they are happy with that. Twofold. First thing is that in training, we need efficient algorithms to solve the optimization problems, as well as to store and process the massive amount of data. Secondly, once a model is learned, its representation and algorithmic solution for inference needs to be efficient as well. So for these two purposes, definitely we need, simply saying, statisticians are very poor in computational power. So without computational power, it is impossible to learn machine learning, that's all. But theory, actually, we will take it from statistics as well as mathematics. So anyway, some of the simple differences between these two things, I can say machine learning, of course, it's an algorithm that learns from data without relying on rule-based program. But statistical modeling, actually, it's a formalization of a relationship between variables usually in the form of mathematical equations. And statistics, of course, are field of mathematics, but machine learning is a field of computer science. I agree to that. But I don't know, people will fight with you. That I can't give you assurance. But it's a field of computer science. I agree to that. That it deals with, of course, building systems that learn from data instead of explicitly programmed instructions. Now, specifically saying, we can say these are some of the differences between that. Statistics actually is a field of mathematics, but machine learning, computer science. Then in statistics, we focus on models with programmed instructions, because some theoretical concepts are there. Using those theoretical assumptions, we are actually reaching up to this building models. But in machine learning, actually, we are creating systems that learn from data. And in statistics, actually, of course, the purpose is primarily making inferences or relationship between variables. But here, actually, we focus on especially on accuracy, prediction accuracy, be frank. That is optimization, of course, because actually there in machine learning, we are actually dealing with huge volumes of data. Then in statistics, of course, prior assumptions, some knowledge about population usually required, but here nothing. Then regarding the dimensionality of data, there actually CS people will score 100%. So the statistical techniques which I am going to share one by one, like a regression, linear regression, logic, most of the people are aware of that among this group. Linear regression or naive-bayes or logistic regression, then decision tree, all these things, actually, these are all not new things or last 10 or 15 years. No. It's actually old, say century back method. Regression, I think, more than 100 years back, that topic was invented. In statistics, of course, we were using those things, but only thing is that statisticians or statistics people is having the limitation of dealing with huge volumes of data. So when machine learning comes, actually, that computational power together, that is theory from statistics, computational power from computer science. So together, actually, this becomes this machine learning or AI or deep learning, etc. These are actually that much emerging area. Okay, so regarding the dimensionality of data, of course, in statistics, we consider only low dimensional, but usually in machine learning, usually applied to high dimensional data. Of course, machine learns from data. Then knowledge, no ML knowledge required, but in machine learning, that is the difference. Please pardon, I can't skip the last thing. For studying statistics, no ML knowledge is required, but to deal with the data set, definitely knowledge is required. But for learning ML, some stats knowledge usually required because it is a basis for algorithms. So these are the basic differences. A lot of other differences are there, especially while using especially technical terms also some differences are there. One of the confusing thing is that the term parameter. In statistics, the word parameter actually corresponding to the word parameter in statistics, in machine learning, we are using the term weights. Then corresponding to the term data point, here we are using the term instance. Then covariate instead of covariate feature. Then instead of estimation, fitting, etc., here we use the word learning. Then in statistics, we use the term regression, classification, etc., etc. Here, supervised learning. Those are, here also we are using these terms, but those things comes under supervised learning. Then clustering, like I mentioned previously, then those things actually comes up. So similarly, some technical, there is some difference between technical terms also in statistics and machine learning. Okay, now moving to, so anyway, just regarding the machine learning model, just I want to conclude for that, give a conclusion for that particular term machine model like this. A machine learning model can be, of course, a mathematical representation of real world phenomena, but it's of course a statistical model, I can say. But I'm not saying that always 100% always in the form of mathematical equations. No. Okay. But anyway, like I mentioned, statistical concepts and terms that are prevalent in this machine learning includes regression, weights, biases, models, etc., etc. And one of the important, I can say, term or word that connects statistics as well as machine learning is predictive. Predictive analytics or predictive modeling. Okay, so I'll come to that. Before that, let's have a look at the types of machine learning. Types of machine learning, traditionally saying we have only 3 types: supervised learning, unsupervised learning, and reinforcement learning. But recently, when we Google also, we can see 4 types. Don't worry, if you skip this also, don't worry. Semi-supervised learning, actually it is a combination of supervised and unsupervised learning. So traditionally speaking, there are 3 types of machine learning. So supervised learning, unsupervised learning, and reinforcement learning. Again, the supervised learning we can classify into 2, classification and regression. Semi-supervised I am skipping because it is simply a combination of supervised and unsupervised. So I am skipping that. So unsupervised, again, we can classify into clustering and association. Then reinforcement learning. Reinforcement learning, usually we use especially, actually the one agent will decide what to do to perform the task. Now come to supervised learning. Of course, it's a learning in which we teach or train the machine, just like the previous example that I mentioned. Okay, just a minute, 1 second. Okay, so supervised learning, just like in the previous example that I mentioned. So supervised learning, as in the previous example, that is teaching a child, say cats and dogs, or teaching a child different fruits. If you are provided with a different images of different fruits, of course we can teach a child by taking those images one by one. Let us take the first image. You can teach that child as this is an apple or this is an orange, something like that. So this is a supervised learning. So same example, that is there actually we start with a training data set. Then we teach that child. After teaching, we will take another set of data that we call as test data. And here, after passing the data, suppose we are passing a set of images to a machine. So after passing those images to the machine, of course, we will get a model. That model can be some mathematical thing or some statistical model. That itself we call it as machine learning algorithm. Okay, so but after getting the model in that example, actually that learned child is equivalent to the model, mathematical model. Okay, so after getting the model, of course, we don't know whether that model is correct or not. In the case of child also, since we are not sure that the child learned to distinguish between dogs and cats, that is why I took another, I brought another dog and I asked that child, what is this? So same thing here also, in machine learning also, we have to take another set of data that we call as test data. Then in the case of child, after testing that child, if the child answered correctly, of course, perfect. In the case of machine also, we have to check the performance of that machine. That is, after applying that test data to the obtained model, we have to check the performance of that model. Remember, we start with the training data set, pass that training data set to the machine so as to come up with a machine learning model, test that model, check the accuracy or performance of that model. To check the performance of the model, of course, different methods are there. I'll come to that while taking regression classification, etc. So this is the usual procedure in supervised learning. I can show you an example. See, a set of data. This is a set of labeled data. In machine learning, one more thing, always we have labeled data. That is mandatory for supervised learning. What do you mean by labeled data? See, look at this example. I have a set of images. So those images are labeled as rectangle, circle, triangle, hexagon. Okay. Suppose somebody there, some child is there who is not aware of these things. Okay, so these pictures or images are labeled as rectangle, circle, triangle, hexagon, etc. So we will pass these pictures to the machine, so that machine will give you a model. Because machine learns from this, some patterns. Okay, so machine will give you a model. We will pass another set of data which is not present in this set. Okay, another set of data which we call as test data to the machine. Another set of data to the machine, then machine will predict whether these set of data as triangle or circle. Sometimes it is correct, sometimes that may be wrong. Okay, so anyway, here it is correct. So we can say out of two images, all the two images answered correctly, perfect, 100%. Okay, but if it is wrong, anyway, after this prediction, after passing the test data, so that it will give you the prediction, test the performance or assess that predictions. It is mandatory. Then only if it is good, if the performance is good, then we can use this particular model for future predictions. Okay, so this is the case with supervised learning. So in supervised learning, actually we teach or train the machine using data that is well labeled, which means that some data is already tagged with the correct answer. So here actually we have some input variables and some output variable, and we use a technique or algorithm just like the form y equals f of x form, just a mapping function from input to output. So simply here the goal is to approximate that mapping function such that we have a new input data that can predict the output variables for that particular data. Okay, so supervised learning, actually it is a task of learning a function that maps input data to output data based on some input-output pairs. Okay, so here actually even the machine, it acts as a supervisor, or in supervised learning we can say the training data provided to the machine works as a supervisor that teaches the machine to predict the output correctly. Or it applies the same concept as a student learns in the supervision of a teacher. So that is why it is known as supervised learning. So once again, here the training data provided to the machine works as the supervisor that teaches the machines to predict the output correctly. Okay. Now, two types are there under the supervised learning: classification and regression. Classification model, actually, this is an example of classification model. Here, actually, we have some categories. Okay, so if you have some categories as yes or no, pass or fail, on or off, or these are actually categories or classes. Okay, so here actually we are predicting whether this is a triangle or rectangle or circle or hexagon or something like that. So classification models or classification problems are used for where output can be categorized. But in case of regression, if the output is a real value, suppose you want to predict the weight of a person, height of a person, BP or salary of a person, or say price of a house, all these things are actually quantitative things or continuous things. So in those cases, actually we use regression. Okay, got the difference between classification and different classification problems we use, because one of the main, especially while applying machine learning techniques, one of the main thing that we are facing, which technique to apply for my data. So the first thing that you need to learn is either supervised or unsupervised. I'll come to the unsupervised. Before that, just get a thorough knowledge of the supervised learning. So if you have decided to apply supervised learning for your data set, just decide whether you need to approach classification problem or regression problem. So if your prediction is actually a category or a class, then take a lot of classification methods are there, many regression methods are there. You can choose any one among that. But before that, decide whether it is a classification or regression model. Okay. Now, this is one of the example for classification model. Another example again for classification model: cat, dog, hen. So training, after training using supervised learning algorithm. Now, what is the difference between unsupervised and supervised learning? I explained the supervised learning. See, same example I can show. See, look at this example. This is actually a case of labeled data. Okay, we have a set of labels. We pass that machine to the model. We pass that data to the machine. That machine will give you a. But if we use the same data for unsupervised learning, what will happen? Listen, you have a set of data. There is no label. So that is why unsupervised learning means training of machine using the information that is neither classified nor labeled. Okay, so here actually simply the task is to group unsorted information according to similarities or patterns or differences, something like that. Listen to this particular example. We have a set of data, but it is unlabeled. We pass this to the machine. No labels here. No labels here. We pass this to the machine. Then what the machine do? Machine will classify this set of data into different groups according to their similarities, according to some similarity or some characteristics. So here actually machine classify this into different groups according to the shape. But if you are providing or if you are feeding a computer different set of images of apple, okay, apple itself, we know that green color apple, then red color apple, sometimes yellow, etc., etc. So if you are passing that those set of images of apples only to a machine, definitely it will categorize into three groups. First group say red apple, second group green apple, third group yellow apple, like that. Okay, but in this particular example, actually machine classified into different groups according to the shape of this picture, and these groups itself we call it as clustering. So this is actually clustering. Clustering is one of the unsupervised learning technique. Okay, so after this grouping, sorting, if you want, you can give some name to this. But initially, we don't have any labels. So that is a, see, look at this here. Do we have any prediction here? No. Simply grouping. or clustering. So that is why previously I had mentioned that don't expect this machine learning outcome always as a prediction. Okay, here we don't, but here actually it is predicting whether it is a triangle or circle something. But in unsupervised learning, it is not like that. It is actually a type of grouping. Okay, and here actually I would like to mention one thing. In the previous session when I joined, I saw in chat actually one question regarding the market basket analysis. Which technique? So actually the technique that father actually mentioned that. So for market basket analysis, actually we are using the association technique in machine learning. Okay, association technique actually comes under this unsupervised machine learning. Unsupervised actually classified into two. See, unsupervised learning classified into two, clustering and association, where the example that I showed you with unlabeled data comes under clustering, but market basket analysis is an example of association technique. Now, what is market basket analysis? Nothing. Market basket analysis. Market means supermarket. Basket means basket in a supermarket. So what is the need of analyzing this particular thing? Basket in a supermarket. Lot of things are there. And one thing, please keep in mind, even though I mentioned association technique is one of the technique which we are using for market basket analysis in machine learning. And in association technique also, one algorithm, we can call it as a priori algorithm. We are using for market basket analysis. And what I want to share is that the only theoretical concept behind that particular algorithm is our probability, especially conditional probability. Now you can ask me, what is the role of conditional probability here? See, what is market basket analysis? See, suppose someone in this group, say, approached a supermarket to buy a list of items. Okay, so if you have a list of items, definitely you will start with a basket. After reaching that supermarket, you will start with a basket. So you will pick items one by one. Okay, finally you will come to that counter. You will pay the bill, etc. That supermarket, that salesperson will give you the bill. You will pay the bill. You will give that. Now, while taking items one by one, suppose assume that you have a list of items such as rice, dal, etc., soap, etc., washing powder, etc., in your list. In addition to that, suppose you have a list of vegetables also in your supermarket, in the same supermarket. Okay, definitely you will buy those vegetables also from the same supermarket, right? You will not use your time to visit another shop for buying that vegetables. And nowadays, most of the supermarket, we can find a vegetable section. So anyway, so why I mentioned that vegetables here, reason is that you have visited the supermarket to buy that items such as rice, dal, etc., flour, etc. Since the supermarket is having the provision to get vegetables also, you selected or you bought those vegetables also from the same supermarket. So there, probability that the items such as rice, dal, etc. already purchased. That is a given thing, given event, occurred event. What is the probability of purchasing vegetables? Given, why we are using conditional probability? That conditional probability, what do you mean by conditional probability? Probability of, say, A given B. A given B means probability of an event A, given that another event that has already happened. So in this particular example, already happened B is purchase of rice, dal, etc. That you have decided to purchase, you have visited supermarket only for purchasing that. But since the supermarket, in that supermarket, vegetables also availed, you purchase that. So that supermarket authorities will find the probability of purchasing or probability of selling those vegetables, given that the other items already purchased. Even though I shared only these examples, how many persons are visiting in a supermarket daily or per hour? How many correlated items are there? Even not only, say another example, I can say, suppose a husband and wife with a small kid visited a supermarket for buying some tin food such as Cerelac or Nana or something like that. They have decided to buy, or they have visited and decided to buy these items from the same supermarket, But if the supermarket, that is a given thing, happened event, that event already happened, purchase of tin food. Okay, but if the supermarket is having the provision to get this diapers, say Pampers, Snuggie, etc., definitely those couple will buy those Pampers or Snuggie, etc., from the same supermarket. So what is the probability of selling that? What is the probability of purchasing that? So similarly, a lot of correlated items are there. The customer will visit the supermarket for purchase something. Given that, even what is the probability of purchasing or selling the other item also? Lot of correlated items. Even not only correlated items, even we can find, or in market basket analysis, actually we are doing the correlated persons also. See, suppose a husband and wife visited a supermarket. Assume that they visited supermarket to buy some beauty items for that wife, for the wife. But when that wife is picking those items one by one, maybe the husband happened to see some shoe polish or shaving set, shaving cream or something like that. Definitely, if he is having a plan to buy those items, definitely he will buy it from that same item itself, from the same supermarket itself. So there actually person to person correlation, husband, wife. Okay, so if the authorities, supermarket authorities will do, supermarket authorities in the sense some data analyst or data scientist persons will be there. If they will monitor or they will do these analysis with those data, because not only day by day, every hour itself actually lots of data are coming from that bill itself. Okay, so those type of analysis, of course, if they will do this analysis regularly, definitely that supermarket owner and concerned authority, they can increase, they will get a profit in millions for the future years, right? Because they can predict what all things to include or what all things to ignore from the supermarket, what all brands to include, all those things. Okay, so that actually we call this market basket analysis, and here we are using association techniques in unsupervised learning. Okay, so that is about unsupervised learning. Then third thing is actually reinforcement learning. Reinforcement learning is actually training of machine learning models, as I mentioned, to make a sequence of decision. Here actually the agent will do what to do to perform the task. Of course, game playing is the most common example. Chess, to predict the winner of a chess, we can use the reinforcement learning. Okay, so it's about actually taking suitable action to maximize reward in a particular situation. Okay, so actually here the agent is supposed to find the best possible path. So I can show you one example. See, look at this example. One robot here. Okay, the aim of this robot is to catch this diamond. But if we come through this way, one hurdle here. If we come through this way, one hurdle here. If we come through this way, one hurdle here. So after overcoming all these, some fire, right? After overcoming all these hurdles, how to catch this diamond with minimum time or best minimum or best path or minimum cost, etc., etc., etc. So the agent will decide what to do to perform the given task, or the agent is supposed to find the best possible path to reach the reward. Okay, so that is about this reinforcement learning. So here in this session, it's very difficult to finish all the things in this 1.5 hours. Sorry for that. But just I'm giving you an overview of these things. Now moving to this classification, regression, etc. So here are some examples of machine learning. Only some examples I have mentioned in 2 slides. Automatic translation, traffic prediction, virtual. So a lot of examples are there, even thousands or more, lakhs and lakhs of examples we can find for machine learning. So due to these examples itself, we can say we can find applications of machine learning in social media, medical diagnosis, finance, marketing, bioinformatics, agriculture, etc., etc., etc. Now, here I have included only 100 plus algorithms. Even you can include not only 100 plus, 1000 plus or 10,000 plus or 1 lakh plus machine learning algorithms are there. But here I am concentrating only these traditional algorithms. But before moving to traditional algorithms, if you have any queries, let me look into the queries also. I think any queries? Just I covered only what is the difference between statistics and what is the difference between statistics and machine learning. Then what is machine learning? What is machine learning model? What types of machine learning? What is supervised learning, unsupervised learning, and then reinforcement learning? Then some examples for these things. Then what are the types of supervised learning? What are the types of unsupervised learning? Okay. I'll share this PPT before. Okay, I'll share. Sure. After the session, before session, no. After the session, I will share it. I'll share with the coordinator. Sure. Okay. Any other? Yeah, I already explained that a priori algorithm. I explained that the case of conditional probability, right? Same thing. Yeah, in a priori algorithm, actually, we are using the conditional probability. Find the probability of purchase or selling something given that another other thing already purchased. Okay, any query up to this? No, okay. Yeah, I know these are, of course, basic things. Since today is the first day, that is why I have decided to go through only the basic things. But even though it's basic things, there are some things maybe, while moving to algorithm, some things may not be familiar to you, especially while taking regression, all those things. Okay. Now, these are the machine learning algorithms. First of all, I'll tell you which of these are classification models, which of these are regression model, or which of these are unsupervised learning. First one, naive Bayes is a classification model. It is based on the Bayes theorem in statistics, where I think almost all the participants are aware of Bayes theorem. So let me start with the Bayes theorem first. Then linear regression, that is a regression model. So these two are, of course, this is a classification, this is a regression model. The logistic regression, please keep in mind, logistic regression is not a regression model, but logistic regression is a classification model. Then decision tree is a model that can be used for both classification and regression. That is, decision tree classifier there, decision tree regressor there. Random forest also for both classification. Actually, random forest actually, if sometimes say some confusing decision trees or multiple branches comes, that time actually we will move to random forest. That can be used for both classification and regression model. Again, support vector machine or simply SVM. Again, it is a supervised learning. All these are actually supervised learning techniques, but support vector machine can be used for both classification and regression models. Next is K-means clustering. From that word itself, it is clear. It is an unsupervised learning. K-nearest neighbor, it is a supervised learning, but that can be used for this, can be KNN, simply KNN. It can be used for both classification and regression techniques. Then these things are actually principal component analysis, PCA. That is one of the technique which we use for reducing the dimension. It is a dimensionality reduction technique. So that's an unsupervised learning technique. Similarly, LDA also. Then while reaching the neural network, actually, we can say that we have reached the deep learning techniques, where of course deep learning is a subset of machine learning. So neural network means artificial neural network or convolution neural network, recurrent neural network, etc., etc., etc. Okay. Yeah, this already I mentioned. That is, in what we do is that in machine learning problem, we will start with training data set, the learning algorithms, then that will give you a machine will give you a model, which we call it as machine learning model. Then we will pass test data set to that model, finally the output. So machine learns from, this is the actually procedure. Machine learns the things from training data set, then apply the knowledge to the test data set. Okay, yeah, this already I showed you. Yeah, classification difference. See here, student profile. Same example itself, we can treat it as a classification and regression model. See, suppose you want to predict whether a student will pass or fail, right? So in that case, you can apply classification model. But if we want to predict the percentage of marks obtained by a student, it is a value, it is a quantitative thing or continuous value. So in that case, we apply regression. Similarly, see, suppose temperature prediction of, suppose you want to predict tomorrow's temperature. If you want to predict the exact temperature tomorrow, definitely we will apply regression. But if you want to predict whether it is hot or cold, or it is rainy or not tomorrow, it is enough to apply classification technique. So that is the difference between this classification. Now, the first one which I am taking here is naive-Bayes classifier, purely based on our Bayes theorem. All of you have studied Bayes theorem in these classes. So this may be the expression which you have studied. So denominator may be a lengthy term. Say probability of here, probability of A is here. Just I have expressed in this particular slide, I have expressed in terms of sigma. But the denominator, you might have studied denominator as probability of B1 into probability of A given B1 plus probability of B2 into probability of A given B2 plus etc. Same thing, same thing. So what is this actually? What is the role of this particular Bayes theorem here? Or how do we apply naive-Bayes classifier in machine learning? Of course, it is a probabilistic machine learning model used for classification technique and based on Bayes theorem. Here actually, some names are there for these terms. For example, left side actually we call it as posterior probability. See, left side, posterior probability. That is A given B or whatever be the notation. Here actually I use the notation H given A, whatever be the notation. Posterior probability means how probable is our hypothesis given the observed evidence. Then right side, look at the right side, three terms are there. Numerator, probability of H. See, that we call it as prior probability. This E given H, we call it as likelihood. That is, likelihood means how probable is the evidence given our hypothesis. See, I can share you one simple example which almost all of you in this group have done that example manually in your either +1, +2 level or in your BTech level. See, one example, there are 3 identical bags, one of which contains 2 white and 3 black balls. Second one contains 4 white and 5 black balls. Third one contains 5 white balls and 4 black balls. A white ball is drawn from one of the bag. What is the and it turns a ball is one of the bag and it turns out to be white, or a white ball is drawn from one of the bag. What is the probability that it comes from the first bag? Or what is the probability that it comes from the second bag or third bag? I am sure that all the participants have done this problem in your school classes. Now, how do we apply naive-Bayes classifier, which is where the concept is Bayes theorem itself, for this particular problem? So definitely you might have done this problem manually, stating the question that what is the probability that it comes from the first bag. Okay, so you'll get a probability. You will stop that problem there. See, suppose instead of that that question, what is the probability that it comes from the first bag? If I'll ask you, predict the best bag. Predict the best one among those 3 bags. Not by looking at the bag. I'm not asking you to look at the bag and predict the best. No. So if I ask you, predict the best one, best bag among those 3 bags, how do we predict the best one using naive-Bayes classifier? It is very simple. You can use the same logic which you have done manually. what is the find the probability that it comes from the first bag using this expression. You have found out this expression. What is the probability? Say, what is the probability that it comes from the first bag means you will calculate probability that B1 given A. Then find the probability that it comes from the second bag, probability that B2 given A. Find the probability that it comes from the third bag, probability that B3 given A. Choose the maximum probability among those. That itself is the best one. Manually, in your school classes, you have done only, or school or college, I don't know, you have done only one part. Here we need to find all the three parts, right? Find the maximum. So here actually, what we do is that the naive-Bayes classifier calculates the probabilities for every factor and select the outcome with highest posterior probabilities. Highest posterior, that is left side actually we call it as posterior probabilities. So highest one among those. So let's just look at this example. See, here two serial number, one column, just leave that. Two columns we have. So this data is actually regarding a code review duration and defect density for not 10, 12 values are here. So review duration, and I have to manage this class in between. I'm taking some water. Otherwise, not tomorrow. Without, I have to go. I told you I have a program. So without sound, no, it is very difficult. That's why, sorry. Okay. So look at this review duration and defect density. Okay. So here, look at this objective. Predict the defect density when review duration is low using naive-Bayes classifier. See, we have to predict the defect density. Okay, when review duration is low, that means review duration is low. That is the given condition. Similar to the example, white ball is drawn from one of the bag. Similar to that white ball, here actually review duration low. That is the given condition. Okay. Then what is the probability that it comes from the first bag? What is the probability that it comes from the second bag? Similar to that, here actually we have to find the defect density. So we have to find probability of defect density given review duration is low. But look at the review duration low. When the review duration is low, we have three options here. Defect density high, defect density medium, defect density low. Three options. So what we do here is that find the probability that defect density is high when review duration is low. Again, find the probability that defect density is medium when the review duration is low. Again, find the probability that defect density is low when the review duration is low. Three probabilities. Here y, I just assume defect density as y and review duration as x. Okay. Then low given low, median given low, high given low. We are getting three probabilities, 0.17, 0.5, similar to three bags, right? 0.37, which these are the posterior probabilities. Find the highest posterior probability, that is 0.5. So 0.5 corresponding to 0.5, we have medium. So in this particular example or in this particular data set, actually, the best option for defect density is medium. The best among three options. Okay, now this particular example, we have only 12 rows, even we can do it manually. Just imagine instead of this 12 rows, just imagine the case of 12,000 or 12 lakhs or 12 million rows. Is it possible to do it manually? No. So that is why in that case, we will approach system, right? So, we will approach the machine learning. So what we do is that initially you will be given a set of data. We will divide that data set. If you have two data sets, then it is fine. One data set at training and one data set test data, that is fine. But otherwise, if you are given only one data set, it is our duty to divide those data set into training and test. Of course, validation, if required, you can use a part of those data set at validation. Usually training test split, we take 80-20, 80%, because more data is required for training. So 80% for training, remaining 20% for test. Or we can use say 70-30, 70 for training, 30 for test, like that. Okay, so naive-based classifier, the theory behind this naive-based classifier is simply this thing, nothing other than Bayes theorem. But only thing is that while dealing with large volumes of data, we don't have the option to do this like manually. So that is why and one more thing. So initially we start with the training data set. The machine will give you a model that we call as here naive-based model. Then we will pass another test data set to that model. Then after passing the test data set to that model, we have to check the performance of that model. Okay, so that is why earlier I mentioned how do we check the performance of models in classification problems. To check the performance, see, this is the procedure. Data, training is split into training and test, then training data set, model development. Then after getting the model, we can pass this test data set for model evaluation. So how do we perform this model evaluation? How do we check or assess the performance of a classification model? Any classification model, either if we use the decision tree as a classification model, then also you can use these performance metrics. If you use a support vector machine as a classification model, then also, or logistic regression or naive-based, any classification model, the performance metrics remain same. These are the performance metrics: accuracy, precision. But all these, some more things are there: sensitivity, specificity, like this, accuracy, precision, recall. But all these things actually comes from confusion metrics. What is confusion metrics? Suppose you have only two options. Say yes, no. Suppose you have only yes and no, two options in your classification model. Okay. In that case, your confusion matrix will be a 2 by 2 matrix. But if you have three options, say yes, no, neutral, or something like that, in that case, it will be a 3 by 3 matrix like that. Okay, let us take this case. So this is the confusion. Of course, a little bit confusing those who are learning this first time. So this is used to evaluate. Actually, from this confusion matrix, we are getting this accuracy, precision, everything. But what is this confusion matrix? Four things are there: true positive, false negative, true negative. Take the case of true positive. What is true positive? See, suppose you have only two options, yes and no. Two categories in your problem, in your data set. Two categories. Okay, yes and no. Assume though that yes as positive, no as negative. These are positive and negative, actually we are assuming. Okay, or if you have 0 and 1, you can assume 0 as positive, 1 as negative, like that. Okay, 1 as positive, 1 as negative. Okay, now true positive means if your actual data is yes and your predicted also yes. Or in this example, see, this is actual data. First row, in the actual data we have high. In the predicted one also, if you will get it as high, you can say true positive. Where positive, you have defined positive as high. Okay, so if you assume yes as positive and no as negative, how to calculate the true positive? How many true positives are there, or how many options are there in your data set with actual data yes, predicted also yes? How many rows are there? SS, like that. Then you can, so true positive means yes. True positive means truly predicted as yes. Similarly, what is true negative? Negative we are actually assuming as no. If we assume negative, reverse also of course we can assume. Nothing wrong in that. Okay, so if you assume negative, no as negative, in the actual data it is no, in the predicted one also it is no. So no combinations. How many no combinations are there? That we call it as true negative. Count those number of no combinations in your data set. Okay, then you can say easily guess what is false positive. False positive. Positive means yes. False positive means falsely predicted. That is, falsely predicted means you have to get the predicted one as no. So count those no yes combinations. Predicted one as no, actual as yes. Okay. Similarly, false negative means no. False negative means negatively predicted, wrongly predicted. That is, predicted data as yes, actual data as no. Count those numbers. That we call as false negative. Okay. So true positive means predicted value matches with the actual value. Then true negative, predicted value matches with the actual value. True negative, same thing. Yes or no only, that is the difference. But false positive means predicted value was falsely predicted. Here also same thing. Okay. Now, all these things are actually calculated from this confusion method. For example, see here actually true positive and true negative are the actual ones, right? Correct ones. Yes as combinations, no combinations. So just add those two divided by sum of all these, we call it as accuracy. True positive plus true negative divided by sum of. Just imagine the case of what is the definition of probability. What is the definition of classical probability? Number of favorable cases divided by total number of cases. That is same as accuracy. This is the thing actually everyone, those who are doing machine learning, oh, I got 90% accuracy, oh, I got 99% accuracy, etc., etc. Actually, that is same as the probability concept. Number of favorable cases divided by total number of cases. Similarly, precision. Precision actually gives us how many, or if we want to check whether our model is reliable or not, it is enough to look at this precision. Then recall. So precision is calculated by TP, true positive by true positive plus false positive. Similarly, recall, then sensitivity, specificity, everything. F1 score means it is the harmonic mean of precision and recall. Harmonic mean means reciprocal of arithmetic mean of reciprocals of these. So reciprocal means only two cases are there. So 1 by precision plus 1 by recall divided by 2. So that 2 comes in the numerator. So just a definition of harmonic mean means reciprocal of arithmetic mean of reciprocals of observation. So if you substitute that, you will get 2 divided by 1 by precision plus 1 by recall. So these are actually performance metrics in classification problems. Usually people will look into accuracy only, but precision, recall, etc. is very important, especially if we have metrics of this confusion metrics of order greater than 2. Now, so that is a case of regression model. Now look at one, that was a case of classification model. Now look at one regression model also. So of course, linear regression is a machine learning algorithm based on supervised learning. But like I mentioned, this naive Bayes or Bayes theorem, then regression, linear regression, logistic, everything actually it is all the more than 100 years old back method in statistics. Only thing is that with this computational power, actually, this is emerging only for the last few years, say 15 years or 20 years. Okay, anyway, so statistically speaking, this regression is used to model the relationship between dependent and independent variables. 2 examples I have mentioned here. So let us look at this first example. We have exam score and revision score, exam score and revision time. So suppose you want to predict the exam score based on this revision time, or you can predict revision time based on this exam score. Anyway, both are quantitative things or continuous value. We can use regression. Here also years of experience and salary. If we want to predict the salary of a person based on years of experience, we can apply linear regression. But these examples are actually only 2 variables here. That is, one variable we use to predict the other one. That variable which we are going to predict, suppose we want to predict exam score, then that exam score we call it as dependent variable or target variable. And the remaining variable, that revision time, we call it as independent variable. Okay. Here also, if you want to predict the salary, then salary is the dependent variable. Years of experience is the independent variable. But since we have only one independent variable here, this we call it as simple linear regression. But if you have more than one independent variable is always one. Otherwise, we have to look at the different predictions or multinomial case. So in simple linear regression, actually, we are dealing with one independent variable and one dependent variable. But in multiple linear regression means one independent variable, one dependent variable, that is one dependent variable and more than one independent variables. If you have only one independent variable, that comes under a simple linear regression. If you have more than one independent variable, two or more independent variables or predictor variables, then we call it as multiple linear regression. So the mathematical form for these two, if you have only one independent variable, simply of the form mx plus c, mx plus c or ax plus b form. So here mx plus c form means m is the slope, c is the intercept. Same as in the analytic geometry which you all studied in your school classes. But if you have more than one independent variable, the model takes the form y equals beta naught. Beta naught is always intercept plus beta 1 x1. x1 is the first independent variable, x2 is the second independent variable, etc. Whatever be the number of independent variables, based on that you can write your model. Okay. Now, anyway, after writing the model, of course, our aim is to find this beta naught, beta 1, beta 2, these constants. Statistically speaking, that is the difference. Statistically speaking, these constants we call as parameters, but please don't be confused with that term. You can call it as some constants or estimates. Okay. So our aim is to find beta naught, beta 1, etc. So for that, actually, we are using a method known as method of least squares. So actually, the best values of these particular beta naught, beta 1, etc. are those for which sum of squares of error is a minimum. That is, when the square of error becomes minimum, you will get the best values. Okay, so that is why one of the performance measure for this particular linear regression is mean square error. So what is mean square error? See, assume that this is a data set. We have three columns: time, temperature, yield. Of course, it is possible to predict time based on temperature and yield, or if so, time, temperature, and yield. So it is possible to predict time based on temperature and yield, or it is possible to predict temperature based on time and yield, or it is possible to predict yield based on time and temperature. Okay, so here I have included this particular objective or one objective. Assume that we have to predict yield based on, say, effect of temperature and reaction time affect the yield, percentage of yield. Develop a model for percentage of yield in terms of time and temperature. Assume. Of course, you can predict time and temperature also. I agree to that. Assume that we are going to predict the yield based on time and temperature. See, all the values are continuous values, so nothing wrong in applying any of the regression models such as linear regression or support vector machine. The support vector machine actually is used for both classification and regression, or decision tree can be used for both classification and regression. That is why we can apply that. That is actually decision tree classifier there, decision tree regressor there. Similarly, support vector machine regressor there, support vector machine classifier there. So that is why, or you can use linear regression, but we cannot use naive-Bayes or logistic regression. For this particular example, we cannot use logistic regression or naive-Bayes because those are classification. Okay. See, if we want to predict, if you are going to predict the yield based on time and temperature, we can assume the model as yield equals beta naught plus beta 1 into time plus beta 2 into temperature. See, I have written here expected yield because that we are going to predict. That is why I included the term expected. Yield equals expected yield equals beta naught plus beta 1 into time plus beta 2 into temperature. Then after applying those method of least square everything, you will get beta naught, values of beta naught, beta 1, beta 2 like this. Beta naught equals minus 67.88. Say beta 1 equals 0.90. Beta 2 equals minus actually it is plus here, model plus, but beta 2 I am getting it as negative. That is why plus into minus is minus. Okay. Now, after getting the model, of course, this is the training data set. You can apply the test data set. You have to check the performance of the model. Okay. What are the performance measures in a regression model? Mainly, two performance measures are there. One is a mean square error. Other is R square value. What is R square value? Or what is first mean square error? Mean square error means, see, time, temperature, yield. These are the initial data up to this column. Time, temperature, yield. See, I have got a model. I have obtained a model like this. Okay. This is the model obtained after applying machine learning. Okay. Applying the training data set. Okay. So in this model, substitute each of these combination in that. That is, for example, substitute time equals 130, temperature equals 190, time equals 130, temperature equals 190, you will get a value. Similarly, next, you will get a value that is same as this 36.185. Okay, then substitute time equals 174, temperature equals 176. In that equation, you will get a value of yield that is 76.1024. So substitute all these combinations in this particular model, you will get these set of values. This we call as predicted value of yield. And this is there in the question, actual value. Actual value, predicted value. Find the difference between these two. We call it as error or residual. See, this is the error or residuals. Another name for error is residuals. Okay, of course, that is a combination of negative and positive values. But we have to make it uniform. So that is why take the square of this error. Again, while taking the square, you have a list of values. Find a representative value, say average. Find the average of those squares. So find the error, square it, find the average. Take the reverse. Just say it in the reverse. Average of square of error. That itself we call it as mean square error. Mean of square of error. In machine learning perspective, the main objective of linear regression is to minimize the mean square error. Minimize the mean square error means actually our aim is to minimize the error. That's all. This minimize the error. Minimize in regression, of course, minimize the mean square error. But in general, we can say optimize the cost function. The error, if you use the term cost function or loss function, so optimize the cost function or loss function. What is this cost function? Predicted minus actual whole square. That is error. Take the square, take the average. So optimize, in case of linear regression, optimize means in case of mean square error, actually optimize means minimize. But in some other actually metrics, we use maximize. Okay. So mean square error, of course, mean square means definitely the minimum value that can achieve is 0. So our aim is to get that maximum, so that minimum value equivalent to 0, nearer to 0 for this mean square error. Okay. So in that case, the model is good or better or perfect, I can say, if it is 0. So mean square error is one of the performance metrics for linear regression. The second thing is actually R square value. R square value actually lies between 0 and 1. What is R square value? Or what is the interpretation which we are getting from? How much our dependent variable can be explained by independent variable. That gives that degree in which the variation in dependent variable can be explained by. Actually, there is of course, it lies between 0 and 1. Usually, if it is above 0.5 or if it is nearer to 1, that means our model is good. Okay. If it is below 0.5 means, that is, if it is lies between 0 and 0.5, that may not be that much good. Okay. Especially if it is 0 means indicate a poor fit. No doubt in that. So R square equals 1 indicate a perfect fit. It lies between 0 and 1. If it's above 0.5 mean it's fine. So actually there is a formula for R square. It is closely related to analysis of variance in statistics. This is the expression for R square. 1 minus RSS means residual sum of squares divided by total sum of squares. Where total sum of squares is this one. Sigma of difference between actual value and its mean of those data. Take the square of that. Residual sum of squares mean difference between actual and predicted. Take the square of that and take the sum of that. That residuals, total of that residuals itself. So I'm not looking into this. You don't have to look into this formula. Just I'm sharing that those who are especially familiar with analysis of variance or ANOVA in statistics, they will be able to catch this. This is simply, I have marked that intercept. Beta naught is this, or not beta naught. Beta naught is this one. Or one more picture I have included here. See, y equals mx plus c. This distance is c, and m is actually y2 minus y1 divided by x2 minus x1. All these things actually you might have studied in your school classes. Anyway, just to show you that. So difference between these actually we call it as error. So anyway, R square value and mean square error, these two are the two commonly used performance metrics. But in addition to that, some other performance metrics also there. I don't know how many of you are familiar with this. That is, after obtaining this regression model, other than checking this R square value and mean square error, if you want to check the significance of your obtained model, you can have a look into this summary. That is, you will get a F value in your table, a corresponding one P value there. If this P value is less than 0.05 means, if the P value is less than P value or probability value, some softwares you will get it as P value, in some softwares you will get it as probability. So if this particular value, P value is a probability, actually it is the smallest level of significance in which hypothesis is rejected. So anyway, if you have to look into only this P value. If this P value is less than 0.05, 0.05 means 5% significance, then your overall model is significant. That is another thing for checking performance. R square value, mean square error. Third thing is overall significance of this model. Again, even though your model is overall significant, again, of course, here less than 0.05, overall model is significant. Again, you can check, even though it is overall significant, you can check whether individual coefficients are significant or not. For that, we use this table. See, here actually we are using T distribution. Here actually F distribution, here T distribution. Look at the P value corresponding to this. For example, intercept always required. Don't look at that intercept. For example, corresponding to this time, my P value is 0.000. Which is less than 0.05. So the variable time is good for prediction of yield. But look at the look at the P value corresponding to temperature. Here I am getting the P value as 0.7, which is greater than 0.05. That means this variable temperature is not good for prediction of yield. In that case, what we do is that you have to find a new model by ignoring the column temperature. By ignoring the column temperature, using this variable time only, find a new model for prediction of yield. Some of you, maybe you can ask me about how that is possible. I have only, see, here actually in this particular example, I am telling about only 2-3 variables, but you may be dealing with large volumes of data set. Your data set may contain, say, 5,000 or 10,000 columns there. Okay, so you have to check the significance like this. Whatever not relevant, not significant, you have to remove those variables, because our aim is to actually get a best accurate model, right? So for that, sometimes you may need to ignore some variables. Okay. So I think time is almost over. So I am stopping here. So similarly, logistic regression there. Logistic regression, actually, we are using this 1 more minute I'll take. See, we are using a sigmoid function. This we call it a sigmoid function. This is the expression 1 by 1 plus e power minus z. So when we draw a graph for this, by giving any value for z, you will get this picture. Okay, it lies between 0 and 1. So usually we predict like this. If our obtained value is above 0.5, that belongs to one category. If it is below 0.5, that is, if it lies between 0 and 1, that belongs to other category. So for example, if you have pass and fail, if your obtained value lies above, say, 0.8, then the predicted class is pass. If it is 0.3, then predicted class is no, like that. Okay. Yeah, this is logistic regression. So logistic regression actually, yeah, this is the cost function. Logistic regression has some relation with linear regression. See, in this here actually, why the name regression comes in the tail of that term, logistic regression. See, here in this expression, Z is same as our linear expression beta naught plus beta 1x or beta naught plus beta 1 x1 plus etc. So that is what I have mentioned in this particular slide. See, here sigmoid is Z, where Z is same as AX plus B or MX plus C or beta naught plus beta 1x, like that. Okay. Yeah, this is three types. That is a binomial case. If we have only two options, yes and no, we use binomial. Or if you have three options, more than two options, pass, fail, neutral, or high, low, average. In that case, we use multinomial. Ordinal means actually some orderly data, we use logistic regression. So anyway, due to limitation of time, anyway, I am stopping here. So participants can quickly ask some if you have any questions. Up to 9:30, right, ma'am?
Yes, ma'am.
Yes, sharp 9:30. Sorry, machine learning, it's very difficult to speak on 1.5 hours. But since the participants are from computer science background, and I know they might be aware of these things. But anyway, if you have any questions, I think all are in the brim of leaving, waiting for dinner.
Thank you so much, ma'am, for that brilliant and insightful presentation. We will now have the question answer session. Participants are welcome to raise their doubts and we shall request our speaker to address them.
Only doubt is link not working. Attendance link not working.
Ma'am, earlier time one posted a query, which evaluation metric is suitable for regression problems?
Yeah, I explained just now. R square value. I couldn't see that question. Yeah, okay. Regression technique, R square value, mean square error. Then if you want, you can check the significance of your model, overall significance using F distribution. Simply look at the p-value. Or if you want only, if you want to check the coefficients of individual significance, individual variables, then you can use T distribution. At least R square and mean square, that is mandatory for regression.
I think no other doubts, ma'am.
Yeah.
Thank you so much, ma'am, for delivering such an insightful and interactive session. Your practical examples and detailed explanation of statistical thinking for machine learning have truly added immense value. On behalf of the organizing team and all participants, we express our heartfelt gratitude to you for sharing your expertise and time with us today. Dear participants, we kindly request you to switch on your camera for a group photograph, please. Thank you. Dear participant, before you log out, kindly take a few minutes to complete the feedback form using the link shared in the chat box. Your reflections and suggestions are very important to us and will help us improve future programs. Now the link is active. Now I invite 2 or 3 participants to kindly share their feedback and experience about today's session. Please.
Good evening, all. I am Pripita BK from Ansa Women's College. I would like to share my feedback on the first day of this FDP titled AI in Action, Bridging Theory and Practice in Data Science and Deep Learning. Today's sessions have been extremely enriching and provided a strong start to the program. The first session on Fundamentals of Data Science and AI by Dr. Father Anil George K. was very insightful. Dr. Anil George explained the core concept in a clear and structured manner, making it easier for us to understand the basics of AI and data science. The second session on understanding data, probability, and statistics thinking for machine learning by Dr. Bindu Krishnan was very informative. It gave us a solid understanding of how statistical thinking forms the backbone of machine learning. Overall, both sessions were well organized, informative, and interactive. They have sparked curiosity and set a positive tone for the upcoming days of the FDP. I sincerely thank both the resource persons and the organizing team of Department of Computer Science and Applications of St. Mary's College, Thrissur for such a wonderful beginning. Thank you.
Thank you, ma'am.
Am I audible?
Yes, ma'am. Yes, ma'am.
Okay, thank you for the opportunity. Our first session was led by Dr. Father Anil George K, Vice Principal and Associate Professor, St. Thomas College, Thrissur. And he began with a simple example of a cooking recipe to introduce the concept of data science, which made the topic relatable. And the demo sessions were simple enough for even a +2 student can grasp. And he also discussed different types of AI research challenges, different learning techniques in machine learning, and the basics of deep learning. And also, the session was a strong and motivating foundation for the FDP. And in the next session, Understanding Data, Probability, Statistical Thinking for ML by Dr. Bindu Krishnan, Senior Statistician, Data and AI, IBM Kochi, was also very informative and insightful. In spite of not being well, ma'am, you have managed the session with great dedication and clarity. You have also explained the role of probability and statistics as the foundation of machine learning in a simpler manner. And your effort and commitment are truly appreciated, ma'am. And the session provided us with valuable learning. And I also sincerely thank the organizers and ATAL for providing us this valuable learning platform and for excellent coordination for today's sessions. Thank you.
Thank you, ma'am. Thank you all for sharing your feedback and experiences. Now we come to the conclusion of today's online program. We had two highly informative sessions, Fundamentals of Data Science and AI by Dr. Anil George K, Probability and Statistical Thinking for ML by Dr. Bindu Krishnan. We sincerely thank both our distinguished speakers for their time and valuable insight. And a special thanks to Mrs. Archana CS for introducing our guests so gracefully. On behalf of the organizing committee, I thank you all once again for your active participation. Wishing you a pleasant evening. Thank you all. Thank you.
Thank you.